One empty railcar travels thousands of miles, burning diesel and eating track time while arriving nowhere. Tallied across North America's freight web, that comes to over 1/3 of every railcar mile logged in a year. Yet the railroads are not doing this out of laziness. So what is really holding them back? The answer reaches into 19th century pneumatic brakes, an engineering standard a century and a half old, federal inspection statutes, and an industry that spent decades picking the cheaper of two costly headaches. It begins with what unfolds inside a mile-long train the instant somebody grabs the brakes. When an engineer sets the brakes on a modern freight, the order does not arrive instantly. It travels as a pressure wave rolling through a steel pipe strung along the whole train, pressurized to somewhere near 90 to 110 pounds per square inch. That pipe is the spine of the Westinghouse air brake, a technology that has ruled North American railroads for well over a century. The pressure dropped the locomotive's brake valve, sets off moves at a deliberate clip, roughly 400 to 600 feet per second in an ordinary service application. Under emergency braking, the wave can hit 900 to 950 feet per second. Even so, none of that is instant for a train running beyond a mile. Take a typical Class 1 consist headed up by an EMD SD70E Ace, or else a GE ES44AC, each past 430,000 pounds and fitted with Westinghouse 26L brakes. Behind them, covered hoppers and tank cars, at 286,000 pounds apiece, build a train that easily stretches 7,000 to 10,000 feet. The moment the engineer calls for braking, the lead cars respond first, their triple valves dumping reservoir air into the cylinders. The wave keeps pushing down the pipe, but the tail cars, sometimes half a mile back, get it a fraction of a second later. On a 10,000-foot train, that gap can reach 15 to 20 seconds between head and tail. So the front slows before the back even knows, producing an imbalance of force. The leading end bunches up, the trailing end pulls out, and the couplers between them absorb the punishment. The effect sharpens when the final car is empty, since its lighter weight hands it a higher braking ratio and less pushback against acceleration. It is like shutting a garden hose at the tap and waiting for the flow to quit at the nozzle. It does not stop everywhere at once, but eases, then ceases, the lag widening with distance. On the railroad, that delay is simply physics, not a flaw in the design. That is the first reason every car in a long train reacts differently once the brakes come on. Air only travels so fast. A lightly loaded car creates a distinct handling problem. Once the brakes go on, its lighter weight lets its wheels react faster to the same force than a fully loaded car. Railroaders talk about two forces here: buff and draft. Buff is compression, the cars crowding together as the front slows ahead of the rear. Draft is tension, the couplers pulling apart as the tail lags behind. Both are normal, but once a consist blends heavy and light cars, that mismatch can flip routine slack action into a hazard. Picture a manifest freight running loaded tank cars at the head and a near-empty boxcar bringing up the rear. As the signal works back, the loaded cars fight the stop while the empty one, with its higher braking ratio, bites harder and sooner. That abrupt shift can throw a surge of tension along the couplers, hard enough to set off a draft event, and the train effectively tries to rip itself apart from within. On the next release, the forces flip, the rear slams into the front, and a buff overload looms. Either outcome can end in snapped couplers or, at worst, a derailment. An obvious fix suggests itself. Just pile extra brake hardware onto the empty car or shuffle the train so each car's weight matches its neighbor's. Reality is thornier. How any car behaves hinges on the makeup of the whole consist, not the gear on one car. And no single change can promise even forces the length of a mile-long train. So why not just engineer the trouble away? The answer is a second, subtler limitation that molded the whole industry for over a century. Back in 1869, George Westinghouse won his patent for the automatic air brake, a design destined to become the backbone of North American railroading. It swept away a jumble of hand-operated brakes and mismatched hardware, replacing them with one continent-wide standard, a single, unbroken steel pipe of compressed air tying every car together. The pitch was simple: braking on every car at once, no matter who owned it or where it was bound. As the decades passed, the Association of American Railroads locked this into rule, requiring every freight car and locomotive to share one identical pneumatic brake envelope and one identical knuckle coupler. That wasn't purely engineering. It was commerce. Holding everyone to one rulebook let the industry sidestep bespoke hardware, special adapters, or constant reconfiguring whenever a car rolled onto another railroad's turf. The payoff was immediate. Trains could be pieced together from cars built by dozens of makers, sent thousands of miles, and traded freely at interchange points with no holdup. Crews mastered one system. Spare parts stocks shrank, and the capital strain of owning rolling stock eased, since any car worked anywhere. Compatibility and simplicity beat any theoretical edge from tailoring each car's brakes to its own weight. But one standard carries a price. Once the whole network had been assembled around the Westinghouse air brake, any change, however encouraging, had to function everywhere, for everyone. The standard's very triumph hardened into a limitation, setting the boundaries for every upgrade still to come. Electronically controlled pneumatic braking, ECP for short, held out a revolution in train handling. Where the classic Westinghouse setup rides a pressure wave crawling through a pipe, ECP brakes run on a digital command cable strung along the whole train, so the engineer's order lands on every car in the same heartbeat. And it is not just theory. In pilot runs, BNSF took a 100-car train to 50 miles per hour and shortened its stopping distance from 4,100 feet down to 2,500, a cut of nearly 40%. In another trial, a 165-car train at 38 miles per hour pulled up in 1,830 feet rather than the usual 4,500 feet. The gains were clear, quicker, more uniform braking, less slack action, less risk of broken couplers or derailments. But ECP's promise collided with an enormous interlinked fleet. Retrofitting every freight car meant mounting fresh electronics, control valves, and connectors on every car and locomotive. The Federal Railroad Administration pegged the bill at $4,000 for each car and $40,000 for each locomotive, adding up to something near $7 billion across the Class I fleet. And the hardware was only half the trouble. The network runs on interchange, with cars owned by dozens of parties passing freely between railroads. When only some carry ECP and the rest do not, trains run in a mixed mode, the ECP edge evaporates, and the digital gear becomes one more layer of complication. The railroads did not ignore the data. They ran pilots, weighed the cost, and the verdict was clear-cut. ECP braked better on paper, but the steep retrofit price and the risk of incompatibility outweighed the benefits for a network founded on universal interchange. Cheaper capital and simpler operations carried the day. Here's the part that blindsides people. Pulling or shifting one car isn't like sliding tiles in a puzzle. It sets off a chain of regulatory fallout that reaches far past the yard. Federal law, 49 CFR, Part 232, requires every freight train leaving its initial terminal to pass a Class I brake test. That's no quick glance. The brake pipe has to be pumped to between 90 and 110 pounds per square inch, and the pressure back at the tail kept within 15 pounds per square inch of the head. Crews must confirm air leakage stays under 5 pounds per square inch per minute, and a qualified person must inspect every brake. Alter the consist by adding, dropping, or even reshuffling cars, and the rules demand the whole train be tested again, redoing the charge-up, the pressure verifications, the leak test, and the whole inspection, whether the change was one empty car or a whole block of loaded hoppers. Picture a real interchange. Railroad. A prepares to hand a consist to Railroad B, 150 miles down the line. Should a dispatcher opt to set out an empty car at some mid-route yard, the train has to divert to a certified brake testing facility, where a fresh Class 1 test is mandatory, piling on hours of crew time and locomotive idling. The paperwork stacks up. Inspectors log the test, revise the consist record, and alert both carriers, and the regulatory clock resets. Leave the consist untested and the train legally can't move. What looks like a minor tweak becomes a formal proceeding bound by federal rule, with pressure marks, leakage caps, and inspection benchmarks that allow no improvising. The consequences fan out across the network, forcing delays, added labor, and paperwork at the next interchange. Practically, it's nearly always cheaper and safer to let the empty car ride than to kick off a new compliance cycle. Why swallow the expense of dragging it? Because the alternative is a bottleneck that devours far more time and money. Inside a railroad operations center, calls get made with a ledger, not a gut feeling. Each time a dispatcher weighs setting out an empty car versus keeping it, the math is about the whole system, not the next mile. Fuel is the first line. A mainline unit such as the EMD SD70 ACE or a GE ES44 AC drinks 130 to 140 gallons of diesel an hour, north of $500 at today's prices. Yet the weight of one empty car, often under 30 tons, hardly moves the dial on a train already dragging thousands of tons. The real cost is disruption. Taking an empty car out mid-route means pulling into a yard, assembling crews, and putting the train through a full Class 1 brake test once more. That idles locomotives, piles up crew hours, and occupies yard room. One test alone can pin 2 hours or more onto a shift, and the knock-on effect stalls other trains waiting for track or inspection, compounding overtime, idling fuel, and forfeited slot time on crowded main lines. Crew time and yard dwell cost far more than the slim fuel penalty of towing an empty car. Railroads think long-term, modeling payback over 15 to 20 years, not one trip. So keeping an empty car aboard isn't an error, but a calculated trade-off the models keep confirming. So what shifted? The price of every mile climbed. Fuel has trended higher for a decade, and collective bargaining has pushed crew wages up, so each extra car now wears a steeper tag than a generation back. And the sting isn't only at the pump or payroll. Towns along the main line have grown less patient with noise and diesel fumes, and fresh air quality rules have nudged railroads to reconsider the length, the weight, and the frequency of the trains they run. Meanwhile, the economic playbook tightened. Precision Scheduled Railroading, or PSR, migrated out of Canadian National during the early 2000s, reaching Union Pacific, Canadian Pacific, and the rest by the late 2010s. With PSR in force, the old fixation on raw tonnage yielded to fresh priorities: dwell time, train length, and asset velocity, with every car judged by how fast it threads through the network. Keep trains rolling, cut idle time, wring more from every asset. To stay on pace, railroads leaned into block swapping alongside unit train operations. Block swapping lets crews set out or gather groups of cars at key yards without tearing the whole train apart, and unit trains, long ribbons of a single commodity running point to point, curb sorting mid-route. Both help, but neither erases the core constraint. Mixed consists and interchange rules still impose compromises where loaded and empty cars ride together. Distributed power is another tool. Systems like Locotrol position remote-controlled locomotives partway back or at the tail, evening out in-train forces and softening the pressure wave, at times trimming the need for an empty car at the end. But it shines brightest in bulk or unit service. On mixed manifests, or wherever interchange partners have no compatible technology, the old limits hold. The system bends only in fragments, and the empty car, for now, still has work to do. Every day, railroad workers carry responsibility for inspecting, repairing, and safely running thousands of freight cars under strict federal standards. A single Class 1 brake test, mandated under 49 CFR, Part 232, calls for a close look at the brake pipe, the valves, and the couplers on every car, whether loaded or empty, done by a qualified individual with exact pressure checks, leakage caps, and documentation. Crews are drilled to catch worn brake shoes, air leaks, and valve faults, since one missed detail can bring consequences miles down the track. Fleet turnover adds another layer, as most North American freight cars stay in service 30 to 50 years. Even as fresh telemetry and wireless monitors hold out better data and predictive upkeep, most of the fleet still leans on legacy Westinghouse air brakes and hands-on inspection, and broad adoption of cheap retrofit kits and digital sensors will take decades, not months. A hesitance to ditch proven habits isn't stubbornness, it's practical prudence. When the stakes are lives, cargo, and federal compliance, the well-worn path looks safest. Change comes, but in railroading, it advances at the speed of trust and the tempo set by the rolling stock itself. These days, every empty car crossing the continent mirrors a calculation shaped by physics, by Federal Railroad Administration brake test mandates, and by the economics of equipment cycles, not unlike a backup battery kept on hand for the sake of reliability. As automation and precision-scheduled railroading keep pressing efficiency's boundaries, the reasoning behind this compromise meets fresh challenges. Still, for now, operational resilience continues to outweigh flawless utilization. Subscribe for more engineering stories that expose the logic just beneath the surface.